What are the solutions when things blow up or when things get small? Okay, so let's first talk about the solutions to the exploding gradient problem. Okay, so in the extreme case, if you run into the exploding gradient problem, and this actually does happen, is you run your PyTorch or TensorFlow or JAX code, and at some point you see infs or nans coming out of your model. Okay, that's maybe an indication that things had overflown. Okay, even if it doesn't overflow, even if you're still managing to train things and it's not exploding massively, you might still run into issues, because in effect what you're doing when you're doing gradient descent is that in effect by having very, very large gradients, you're in effect taking very, very big steps in your parameter space. And if you've looked at my video on gradient descent, you will see that if you take very, very big steps, then sometimes this actually screws up the gradient descent optimization procedure. Okay, so even if you're not getting infs or nans, you might still be basically not training your model in a good way, because you're taking these very big steps because of your exploding gradients. So the solution to this, limit your gradients. Okay, so you can implement something called gradient clipping. And what gradient clipping does is it looks at the norm of the gradients, and if that's larger than some threshold, then it just scales the gradient down to have a norm that's equal to that threshold. Okay, so you're basically going to squash the size of the gradient so that it's more reasonable. You're still going to take a gradient step in the same direction as the one that you've calculated. You just make sure that that step isn't as big as the value that you calculated. Okay, does that make sense? Super easy. So in PyTorch, I think there's a gradient clipping thing, and you might need to specify a threshold, but you probably just pick the one that's in there already. Vanishing gradients is somewhat tricky. Okay, so let's just recap what is the vanishing gradient problem. Okay, so here's a little sentence that we might want to feed into an RNN. Okay, so we have the sentence, and I'm going to ask you to complete it, so read it carefully. When she tried to print her tickets, she found that the printer was out of toner. She went to the stationery store to buy more toner. It was very overpriced. After installing the toner into the printer, she finally printed her tickets. Tickets is right, okay? So you've got this word tickets here that are like, I don't know how many time steps in the past before you're predicting the next word, okay? And so if this is your training data, tickets will probably have a very small effect on the tickets here, even though it should maybe have a big effect. Okay, and so the problem is if you've got vanishing gradients, then things that happened way in the past can't affect the current output. So with the vanilla RNN, you're going to run into issues if you do this. Make sense? Just nod? Okay. And so the strategy that we follow to address this is to normally change the architecture of the RNN itself. And you've probably heard these words before, words like long short-term memory, which is an extension of recurrent neural networks, and then gated recurrent units, which are slightly simpler than LSTMs, but are also an extension of RNNs. When I train models, I normally start with GRUs. I just find them easier to train, and then at some point I would switch to LSTMs and see if they work slightly better. And these days, with the toolkits that you use, it's normally just changing a few letters, and then you get one model instead of the other. Now, I can spend a whole lecture talking about LSTMs and GRUs, but instead of doing that, I'm just quickly going to help you become experts. So the way you become an expert in LSTMs or GRUs is we pause this lecture, you go and read Kola's blog, okay? You finish Kola's blog, and you are done, and then you are an expert in LSTMs and GRUs. It's an excellent blog, you read it, and you understand these models. And I'm guessing many of you have actually read it maybe in the past, or at least have come across it. Okay, so you can go through that blog. I'll quickly summarize the key insight for why this actually fixes the vanishing gradient problem. As a quick reminder of the vanishing gradient problem, we have this thing where we repeatedly apply the same matrix at every time step when we're calculating the error signals. Okay? And the question is, how does something like an LSTM or a GRU, how does it fix this problem that inevitably things will die away or explode if you have this recursive thing happening at every one of the error signals? Please go and read the blog, and then you will understand many of these things. But the crux in GRUs and in LSTMs, if you've gone through the blog, is this line running at the top of each of these cells, of each of the LSTM cells or the GRU cells. And the cool thing about this line running at the top is you don't have any matrix multiplication influencing this line. So you get away from this repeated application of the WHH matrix as you have in a standard RNN. So very, very quickly, what you would have in this top line, and this will make more sense if you actually go through the blog, is you've got the previous, I think it's called a context vector sometimes, and then you've got, as the output of one of these cells, you've got this vector again, CT. This is in addition to the normal hidden state and the normal hidden state that you get as in a standard RNN. And this thing is calculated as you take something called a forget gate, which is a little vector, and you do an element-wise multiplication with what has happened before. So this little part that happens here. You take what happened in the previous time step and you multiply that with the forget gate. It's an element-wise multiplication. This vector has values between 0 and 1. Okay, so you're just amplifying well, you're not amplifying. You're either letting it through, which would be a 1, or you're squashing that signal. And then what you're doing is you're adding to this, I think it's called the input gate, which is element-wise multiplied with some other vector that you get inside the neural network here, I think there. Okay. And the idea here is that basically what this line says is, how much should I forget what happened at the previous cell, and then update this with something that happens at the current time step? And how much should I update this like C line with what's happening at the current time step? Okay, does that make sense? Now, how does this solve our problem? Maybe the quickest way to explain it is that the partial derivative of CT with respect to CT minus 1, which is what we would need in order to get the error signal for CT minus 1. This is actually quite simple, okay? There's no CT minus 1 in here, so I can just chuck that one away. So that doesn't have effect when I take the partial derivatives. And then I've got here this element-wise multiplication, okay? And you can guess it's something with FT. Again, if we use the guess from the scalar case that Ryan gave us before, you can guess that the partial derivatives is something to do with FT, and it actually turns out that it's a diagonal matrix that has on its diagonal part, it has the values of FT. Okay? You can find that on Wikipedia if you go through the matrix and vector calculus list of identities. Okay? Now, what's crucial here is, at time step 1, you have the cell, so you have diag FT. At time step 2, you have the cell, diag FT. So every time step, you're multiplying with this thing. Just as in the linear RNN, we kept on multiplying this matrix. And at every time step, we multiply, 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 multiply. In a similar way with the LSTMs, you're going to multiply, 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 multiply. There's one big difference. And this is that at every time step, this thing will actually be different in the LSTM, okay? Because it depends on FT. Where with the linear RNN, this thing was the same at every time step. And now the cool thing here is that the LSTM, or the GRU, at every time step can decide how much to let through to the next time step. Okay? So this FT can, maybe in a whole bunch of time steps, can just be once, which would be I let through everything that happened before directly, and that means that something that happened at time step 1 can, in principle, influence something that happens at time step 150. If I keep on just having a FT here that's just all ones. The LSTM can also decide, based on my inputs at this current time step, the LSTM can decide, okay, no, don't let any of this stuff through. I don't care about it, forget everything. And that's the basic principle that allows something like an LSTM or a GRU deal with this vanishing gradient problem. Does that help? Okay, excellent.